So let's start. First speaker is Sudakov.
So it's a very pleasure to be here. I should really say that it's an amazing workshop and thanks to organizers for inviting me, so many people, so many interesting talks. So I hope to add one more to this list. So I'm going to talk about some simple sounding problem in extremal set theory, which surprisingly, at least for us, had a connection to another area of research, combinatorial optimization. So let me start by reminding you, so the classical questions in extremal set theory, at least there is a really big body of results which sound like this, and where algebraic tools actually were very useful. It's about maximizing the size of set system with restricted intersection. And so here is an example. Let's say it was proved by Berlikamp in '69. The results in this area sounds like this. So if F is a set system on the ground set of size n, such that every set in F has odd size, but intersection of any two sets has even size, then the size of the family. So they cannot have many sets of even odd size such that pairwise intersection. And there are many results of this sort. So you tell me restriction on the pairwise intersection, and I want to show you that there are much less than 2 to the n sets which satisfy this. And many of these results proved using algebra. I want to study a seemingly same sounding question, but it's a little bit different. So this is a question. I'll give you first a baby version. So again, I have set system. Maybe for convenience, I denote it like that. So this is my sets, right? They're all. And now I tell you two things about that. So first of all, I tell you that very much like that, that intersection of any collection of them is odd. I tell you also that the ground set is even. And moreover, I tell you that the union of all sets equals to the ground set. So basically, every element is covered. And I want to ask now, not to maximize the size of the set family, I want to ask you the simpler question: is there such family? Is there such? So are there sets such that all intersections are odd, the ground set and even, and you cover this ground set? Now, it's very important to put this restriction that you cover the ground set, because otherwise you can easily construct such a family. Think about taking sets, let's say, of size 3. So here's 3 sets of size 3. They're all pairwise intersection and triple intersection have one family. But if I, right, and my ground set has size 7, so if I don't insist that it's all covered, obviously I can trivially add your element here, and I will get such a family. But it looks like if I'm not allowed to do this, then the answer is no. If you play a little bit, the answer is no. And here is indeed proof of it. Right, so proof of it. So what would be the proof? So since I know that the intersection of all sets is odd, so in particular there is an element in all sets, so there is x belonging to fi for every I. So then what I do, I take set fi prime, it's fi minus x, right? So I delete one element from sets, from all of the sets. Now these guys, fi has even size, fi prime, even size. My new n, right, n minus x has odd size. And now what we'll do, and I know that, right, that the union, right, the union of my sets fi, right, if I take all of them, it gives me the whole ground set. So the size of this guy is n minus 1. And I write formula for inclusion exclusion, right? So you know that the size of the union is equals sum minus 1 to the power I, size of I wise intersections, where I runs from 1 up to 2. Right? So you basically do inclusion exclusion. So inclusion exclusion formula says you take cardinality of f primes and minus pairwise intersection plus triple intersection. But note that I know all these numbers, they are now even, right? Because they were odd before, and I subtracted one element from each of them, right? So now you get odd number equals even, so contradiction. Any questions of this kind of an important thing? So again, if you have sets which cover everything, the ground set is even, sets are odd size and all, right? So basically you can assume always in my talk that my family is closed down with respect to intersection. So if two sets are there, I will add the intersection to the family for free because that would not violate this condition. I know that all intersections starting with the size of the set, so intersection even of family of size 1, they're all odd. So then I claim that there is no such family. Okay? So I want to consider a more general question of this sort. Okay? Is this clear? So here is a definition of m minus 1 system. And so what would be m minus 1 system for me? Again, it would be family of sets of n element set. I will have integer m, and then I will have a bunch of the conditions. So first of all, I will know that f is closed under intersections. So any intersection of sets in F is again in F, right? So I give you this for free because you'll see I can always add them. Then the second thing, I would know that every set in F has cardinality different from the ground set modulo M, right? For every F. So it's exactly like in this picture. All my sets were odd, and the cardinality of ground set was even. And the third thing, which is very important, for every subset of the ground set of size at most m minus 1, there is f in F containing this set. Right? Again, it's exactly, so if you think my m is 2, this is precisely previous problem. Right? So I really need, in the previous problems, that every one element subset was covered. So it's very easy to see that if I want to have the question of this type, if I go to bigger residue, right, bigger M, I need to be guarantee that I cover all subsets of size up to m minus 1. Otherwise, very easily I construct such a family. And again, the question is there m minus 1? So as I said, it's seemingly simpler question. I really don't care how big it is, right? First construct me at least one, right? So in this case, it's not possible. So I want to know whether it's possible in this case. So again, it's sets which are closed under intersection. The ground set and sets in my family have different residue mod M. And moreover, every subset of set m minus 1 is covered by one of the sets. And I want to know, can you do this?
What was n? Oh, n is the
N
size
is
of
the
the
ground
universe.
set, right?
Okay.
So n is the size of the universe, m would be my residue. Now, obviously, it's naturally, you should ask me why it's all looking at this question. I mean, it sounds maybe nice. Actually, when guys came to me, right, it's a joint work with Martin Negel and Rico Zeklus and my colleagues in the optimization group. So I saw that when they told me that they have a question about set system with a stacked intersection, I said, oh, I probably know most of the things about this type of question. And then I was very surprised to see this question because I saw it first time. I don't know if anybody else saw it before. So why we care about this? So the reason why we care about this is the following. So there is a very classical topic in combinatorial optimization, which is called submodular function minimization. Orit mentioned this in her talk. So let me write submodular function minimization. Right? So I have a function f and the subsets of n element inside. Or you can take a lattice inside the subset, but let's for simplicity assume that this is just all subsets. And this function is submodular, which means that for any two sets A and B, f of A plus f of B is bigger or equal than F A union B plus F A intersection. And the problem is submodular function minimization. I probably, just to save time, will only write this abbreviation. I want to minimize. Right, so this is a very classical problem. For example, min cut is like that, and there are many other questions which you can put in this lecture. Right? So again, you have a function of a subsets which have this, satisfies this inequality, and you want to minimize f. And it's known, it's a very classical result, that if you have oracle, which basically tells you the value of the function over the set you are interested in, this is a polynomial type. Right? There is an efficient algorithm.
So by minimize f, you mean find the set?
Find the set, right? Find the set which minimizes f, right? Minimize f, right?
Yeah,
over.
sure.
So because this problem appeared very naturally in many contexts, that people were interested to know what constraints we can add to this problem in such a way that it still stays polynomial. Right? So I want to look on constraints of modular function minimization, and I want to know under which constraint it stays polynomial. So it's actually not clear, right, what type of things you can do. For example, there is a result of Svitkina and Fleischner, like 2018, which says that with single cardinality lower bound submodular function minimization is hard, right? So what does it mean? So if in addition I tell you just minimize over all sets whose cardinality is at least something, that's already a hard problem. And again, because it's an oracle model, they really, it does not depend on P and P, so they have an argument which shows that you cannot solve it efficiently. On the other hand, there is a very celebrated result from 80s by Grocher, Lowas, and Kreiber, 1981, which says that minimizing f over odd, or let's say even sets is polynomial. So if in addition you require that your set which is a minimizer is odd or even, this is polynomially solvable. It extends a large body of previous result by Padberg and Rao and Barak-Honet and Forti, who were interested in minimizing odd and even cuts and cuts. Now, one interesting thing just which I want to mention, again, it was a surprise for me when Rico told me, so this problem recently became very useful for integer programming. So there is some recent result which so you take an integer programming, so you're trying to application. Mention you're trying to maximize, let's say, C transpose times X, modulo constraint 8 less or equals than B, where the X is integer vector. And you want to know when you can solve this efficiently. Generally, we believe that this is hard. There is a very classical example which says that if the matrix A is totally unimodular, which means the determinant of all submatrices is plus minus 1, you can do this. So recently they extended it to the case where the determinant of every submatrix is from -2 to +2. And to do this kind of result plays an important role there. So therefore it's a natural question to see if we can further extend this type of approach and kind of obtain submodular function minimization, restricted submodular function minimization, which is still polynomial. So let me come to the problem. So let me call it constraint, congruency constraint submodular minimization. Right? So it's a So again, I have f, right? Submodular, and I want to minimize f over set S such, have a space, such that cardinality of S is R mod M. So M is an integer, R is at least say from 0 up to like some basic. So I want to minimize F over subsets which have certain residue.
The algorithm of DLS uses the lead sorry. So is there a strongly polynomial algorithm for this odd even case?
Actually, I have no clue. I need to check.
Because for the usual one there is a strong.
Right. For usual ones, there is this work of Skyver and Fleischner. For this, I don't know.
And when we're talking of polynomial time here in the second case, do we want polynomial in MR or
Right,
is a constant?
right. That's MR as a constant.
A
M is a
constant.
constant, right?
M is a constant.
Right,
Okay.
M is
So if it runs in time doubly exponential in M, that's okay.
But M should not be an exponent, right? So doubly exponential, but the exponent of n, right? So I want n to the power, which is some some kind of good dependence on m.
Okay.
But actually, you'll see that would not be. So that's a problem we want to discuss. Right? So we want to know if, right? So the result of Gochelovsky was m was equal to 2, and then you could have chosen either r to be 0 or 1. And so the new result, which I want to present, this is this. And myself, is that if m is p to the k is prime, then this concurrency constraint submodular minimization can be solved in time bigger of n to m plus a constant. Right? So there is no exponential dependence. It's very honest. Okay.
And that's for any argument, correct?
Right, for any R plays no role here. Right? You choose the R plays no role. Right? That's smaller than n. Okay, so that's the result. Now let me remark you here we actually can prove a somewhat stronger result here, which has application because there were some open problems which people ask in that respect. So instead of doing set, we can actually do more. So you give me a bunch of sets, right? So actually what you can do is a bit more. So we can do one can solve, so minimize f, and then right. So you give me, given u1 up to ut, you give me some sets of your ground set, and then you're trying to minimize f of s such that s intersect ui equals ri mod. Yeah, right. So actually you can give me a couple of such constraints. You can tell me I want my set to intersect this set with cardinality, which is certain number mod m and so on. And this is yes.
Still about the original problem or your version. There's a very natural thing to do, which I expect is naive, and there must be counterexamples. You minimize some modular function without any constraint. Say you want an odd one, say you get an even one. Is it possible that the odd one must be an extension of one value?
So in certain sense, right, that's roughly, it's a very good remark, so that's roughly how the algorithm kind of works. You just need to prove that, you know, that there is certain extension. So let me present exactly in a spirit what Avi said. Let me present an algorithm. So I should say that this is extension of algorithm which Michel Gormans, I don't remember the second person, this his course I had. So it's kind of the idea of this thing is comes from Michel Gormans. So what you do, you go over all subsets A and B of your ground set. Right. So both A and B size at most m minus 1. And they distribute. And so it's roughly what Avi was saying, so you're kind of minimizing maybe over some subsets, and then you can add to them an element or two elements or three elements to get the right cardinality, but it's a little bit more involved. You also want to be disjoint from the set B. So basically what I do, I minimize f of S over sets S which contain A but disjoint. So now it's classical submodular minimization because it's just all subsets of n minus b, which contains a, so it's really can be solved in polynomial time. Moreover, you can output me the minimizer, and since we're working with submodular function minimization, intersection of minimizers is again minimizers. You can output me minimizer of the minimal size, right? So you not only can give me a set which minimizes a function, but among these sets you can give me the smallest one. So let me denote, so let SAB be a minimal size set which minimize this problem. So you look on all sets which minimize this problem and you take the one which is minimal, and then what you return FSAB, which is minimal and has a right minimal among like SAB equal R mod. So you look on all minimizers, you look which one of them has a right cardinality modulo M, right? So you solve all such problems. Right now you see from where n to the 2m comes. So there are roughly n to the 2m such subsets. For each of them, it's just the usual submodular function minimization. So this is this constant of 1.
So then it is strongly polynomial. You worried before.
No, this is right.
Yeah.
Right. That's true. Right. I mean, I don't know what the original algorithm of Krochel, Lovas, and Skyler. This would be strongly polynomial because we're only using
black box.
black box submodular function minimization. So for every such problem, we find the minimizer of minimal size. We look which one R mod M, and among them we choose. So this is algorithm. So the question: when this algorithm works, and what its relation to this problem?
So two things. So does the submodular minimizer find the minimal set in strongly polynomial time?
So you can find the minimal set, right? Again, because the minimizers are so that the intersection is again a minimizer, so the algorithm can output you not only the minimizer but the set of minimal size. Right?
Okay. And over here you don't. You have to prove that this minimal. There is even a single set of size R mod M.
Yeah. So there might be no right. Very good question. There might be you do this, and there might be not sets of size R mod M, and there might be a set of size R mod N, but you output it, but it gives you nothing, right? So the question is, what can we say about correctness of this algorithm, and how it's related to the question which I wrote here? And I think this is a kind of the most exciting part here. So what we proved is two theorems, or actually theorem which has two parts. So the first part says that if there is no m minus 1 system, algorithm works. Right? So if you know that for your m, such systems do not exist, this algorithm outputs you a solution. Now obviously, to have some positive result, now you need to tell me that such systems do not exist. Now note that we already, in particular, if you believe me that this algorithm outputs a solution, we proved this theorem of Krochel, Lovas, and Scriber, because I showed you that m-1 systems do not exist when m is 2. Right? But, so a more general fact which we managed to prove is that if m is a prime power, when m minus 1 system do not exist. Sorry, you want to
In the part we say you can solve given u1 to ut, but then in the algorithm those are not mentioned.
No, this is not algorithm for this problem, right? So this is an algorithm for the first problem I mentioned. You can modify it in very similar spirit to solve, right? And then of course the running time will have also t inside, because you will have t tuples of sets AI, pi, right? But if t is constant, it's still okay. Right? So any questions? So that's what kind of was the motivation to look on the systems. And now when we know that at least some of them do not exist, we will get an extension of the result of Cauchy laws.
For composite M, they do exist.
So that we will talk in then. This is a very good question. Like you will see some ideas and then I mention something in then. Any questions so far?
What are A and B here then?
Sorry?
What will be the choice of A and B?
No, you go over all possible, right? So you run, it's over all possible A and B. So from your old ground set, for all subsets of size m minus 1 pairs, so there are roughly n to the 2m such pairs. You fix A, you fix B, and now you run this algorithm. Right? You look on all subsets which contain A but disjoint from B. This is a usual, this is a new set, right? This is a set of size n minus size of A minus size of B. You look on all subsets of the set, you run the submodular minimization, find the solution of minimal size, put it in your database. When you get all of them, you go all over them, find which one of them have right cardinality, then compute the values and pick the smallest. That's all.
So, is it clear there's always something of the right cardinality? Or
Yes, again, this is a theorem. By no means it's clear, right?
But is that the only way the algorithm can fail, or you'll also?
No, if n is not of this sort, then algorithm can fail in several ways. We don't know it, right? But what we know is that if you tell me that there is, so basically if you tell me that the algorithm fails, I can produce, right? How you prove such a result? So if you tell me that the algorithm fails, I can produce you from this collection m minus 1 system. Right? So that's why this kind of comes natural here. So I look why algorithm fails, what minimal sets it outputs, and somehow I will produce you a set system such that ground set would be not R mod n. So all sets would be. So actually, it's more. So you'll see that if we have only one residue, it's a very easy problem. I'll show you now. So I will produce you a ground set whose cardinality mod m is different from the size of the set. The system is closed at the intersection, and that's beside m. Okay. Any questions?
So was it known when your colleagues came to you and asked you this question? Did they know that you should go for Pm as prime power?
No, they just so I should give full credit obviously to Martin and Rico. So they had this idea to look, because it's a very natural algorithm, as I said. That Michel had a similar things. So it was natural algorithm to consider, and somehow it's very simple. So this proof of this thing is like two lemmas, each maybe 1/3 of a page. It's not complicated. Maybe half a page. It's really not complicated. And then I realized that there is this problem. And when I saw that, when they told me, I thought, oh, sure I can help them. And then I saw that I never saw this problem before. Right? It's interesting when we start playing with it. It's I think it's a nice problem. And you'll see it will fit a little bit the framework of this workshop, because the way we solve it has algebraic flavor. So now I want to give you some proofs. Again, they all would be very, very elementary, right? So once you get the right idea, and then I talk about composite modulo and limitation of what we have. So let me start with a toy case, right? So we said that the ground set and the sets have different residues mod m. So suppose I tell you that all sets in my family have one residue mod m, which is not the same residue, which is a ground set. Yes. So then I claim that this is an easy case, but it would be a very useful case. We essentially solved this case when I gave you illustrated example. So I want to look on my set system. And such set, there are several things, right? So first of all, n is not equal r. Okay? So you have some residue, and you know that your ground set is not, let's say, if n was 2, that your ground set was even, right? So n is not r mod m. For every f in f, the size of f is r mod m. And moreover, f is closed under intersection. But all sets and all the intersection have. So then claim then there is no such. So I claim that we more or less saw this proof, but let me remind you what we did. So here is again the proof. So I take x intersection of all sets f belongs to f, right? So they have some intersection. And moreover, I know that if you take intersection of everybody, this set x is r mod m, right? So now I will delete x from everywhere. So let's come to the new, so let's denote f prime to be f minus x. And take ground set n minus x.
How do you know they all intersect?
Because there's a cardinality.
Because the cardinality. Right? If x is empty, it's perfectly okay. Right? It really doesn't matter. Right? So let us say a system which is closed on the intersection. I look on the intersection of all the sets. I know that this intersection have r mod m. R can be 0, so therefore this would be 0. It's perfectly okay. You'll see that actually 0 would be generic case. Right? So I deleted this x from all of the guys. Now I have f prime. Now what is the size of f prime? The size of f prime is now 0 mod m. Because I deleted the set of size r mod m, and all of them has r mod m, so they now 0 mod m. And I'll do exactly the same thing as before, right? Actually, in this case, it's very important. I forgot to include here, right? We have this thing we have in S. M minus n. So I want to cover all subsets, but in this case I even don't need to cover all subsets of size up to m minus 1. I just need to cover all the points, right? So maybe one more thing, that union of all f is a constant, right? So we always have even more than that, right? We know that we cover all subsets up to size m minus 1, but I only need here that the union of the guys is a constant. Right, so again, I took the intersection, I removed them from the sets, and now I have new sets whose size is 0 mod m. Right, they closed under intersection as before. So therefore, all subsets now have 0 mod m, but my ground set now is not 0 mod m because my n was not r mod m. And then again, I do inclusion exclusion, right? So I take the size of my ground set n minus the size of x, right, should be equal the union of all f prime, which is equals by inclusion exclusion sum over I runs from 1 up to the size of family minus 1 to the power I, and here's the size of I wise intersections. Right, so this is a usual. But I now know that all the numbers here are 0 mod m, and this number is not 0 mod m. But this is 0 mod m. So I get a contradiction.
What was special about the toy lemma? Is the n not equal to r mod m?
No, the special thing was that the all sets, not only they different from n in what residues they give mod m, they give the same residue. Right? And this would be a crucial thing, right? When n was 2, there were not too many residues. It's either 0 or 1. Right? If I tell you that my n is even, and my all sets do not have the same residue mod 2, then they all have 1, and therefore they was immediately the same, right? And that's why the case 2 somewhat easier, right? Because it's a precisely toy lemma. But now I'm telling you something else, right? So remember, our original problem is not like that. Again, I have a ground set, so we can always, by adding extra elements to all the sets, we can always assume that, let's say, ground set is 0. Right? So let's assume that in our setting, right, so here, we can assume that n is 0 mod m by adding elements. To all sets, right? So add some elements to all sets, and then you make your ground set to be 0 mod m. So now I have a different situation. The general situation is different. My ground set is 0 mod m. My sets are not 0 mod m. That's all what I'm saying, right? If your m is, I don't know, 7, then they can have residue 1, 2, 3, 4, 5, 6, not 7, right? They're not the same thing. If I would have been lucky and they would have all, 1 mod 7, then I know that such things do not exist. But now I somehow need to deal with a case when they have different residues, but none of them is. Any questions? So I'll keep this thing here, and so here is a simple idea how you can attack this problem. So you say, okay, so I know this toy lemma, right? So I know if they would have all the same residue mod m, we're finished, right? It's very simple. So maybe I can take my original set system. You give me the set system. You tell me it exists. Here it is. So I take this set system and somehow transform it in such a way that A, the ground set will stay, it will be new ground set. It will stay 0 mod m. My new set somehow magically will become all having the same residue mod m. And moreover, I need to cover everything, right? So can we do this? Now if you start thinking, let's take a very basic case. N is prime, right? And now if you think about n is prime and you have this idea, you immediately realize what you know from your, undergraduate math, that if you take a number, right, and you mod prime, and you want to make it more or less the same residues, that all non-zero numbers will give you the same residue, and 0 will stay 0, you just take it into the power m minus 1. Right? So if somehow I can transform my system such that the size of all cardinalities will become all cardinalities to the power m minus 1, I done. Right? And so it's very easy to do this. So basically what I want, right, maybe set transformation. So I want to introduce set transformation which will transform cardinality x to the cardinality x to the power n minus 1, where x is a cardinality. And once you think about it, there is a very easy way to do this. And actually you will see that this condition about that I cover in the original problem all subsets of size m minus 1 come very naturally here. You see why you need it, right? So how to do this is just a Cartesian product does it for you, right? So what we'll do, so we will have a function, so let me just follow my notes. So we will have a function g, right, which transform all subsets of n element sets into subsets of big n element set. And my big N would be small n to the power n minus 1. So in particular, if n was 0 mod m, then big N is also 0 mod m. So now what would be the transformation? Transformation would be very, very simple. So if you have a set f, so g of f would be just Cartesian product of f with itself, m minus 1 times. So let me write what this is. So this is all e1, e2 up to em minus 1, such that ei belongs to. Right? So from every set f, I create you a new set which contains m minus 1 tuples of elements of the ground set, and all EIs which we have, any m minus 1 tuple like that is a subset. So you just take a Cartesian product of set with itself, m minus 1 tuples. Now obviously, what is the size of GF? It's the size of f to the power f minus 1, and therefore the size of GF for every f would be 1. Because before, right? It was not the ground set, so it was not 0. So it was non-zero number, m is prime, so it's a 1. Okay, so but now you need to kind of see all the other things, and the system which kind of remains the system you want it to be. So observe several very simple things. So first of all, note that we have very good understanding in this transformation what happens if we take two sets, take their images and intersect it. It's very easy to check that it's the same thing as first intersect sets and then take images, right? Because if you see what lives here, here lives vector of length m-1 whose all elements are in F. Here it lives a vector of length m-1 whose all coordinates are in F prime. So if this vector belongs to the sets, you know that every coordinate were both in F and M prime, so therefore it lives here, right? So therefore our system, the new system, right? So we know, so corollary, so if you take this G of the system F is also closed under intersection. Right? And now the last thing, and it's a kind of the nicest part because you see why you need m-1. I want to say that this system, right, the claim which I want to make, that the union of G of F over all sets, right, that if you take, after transformation, you take the union of all sets, you cover your ground set. And why this is so? So what was my ground set? My ground set, right, so here's a proof. So what was my ground set? My ground set was n Cartesian product with itself m-1 times. Right? Take some guy here, right? Some vector x1 up to xm-1. So every xi was an element of your ground. You know that if you think about them as a set, right? Maybe two elements appear several times, but definitely if you now look on S being the set with these elements. Right? Look on this set. So, and I'm looking on it as a set. So if the element appears twice, I don't write it. But obviously, since the total are at most m-1 elements, I know that my S is of size at most m-1. So since my S is of size at most m-1, there was in my family covered all subsets of size m-1. So there was in my family, right? So this implies there is an F such that S is a subset of F. But then, if you know that F contains all these guys, then obviously, according to how I do the Cartesian product, this guy belongs to G of F. Because G of F was a Cartesian product of F with itself. So now, what I have the following transformation. You start with m-1 system over n, right? And you get here a system over n, which is n to the power n-1, such that all sets F size 1 mod m, and they cover ground set and cover. Do you know that such things do not exist? This was Toy lemma, right? So Toy lemma said you cannot have a family of sets whose residue is, let's say, 1 mod m, and the ground set is 0 mod m, and the family is closed down. Right? That's a contradiction, and therefore this proves the practice. Any questions?
I'm trying to digest what U1 comma E2 means. Like,
this is really like a vector, right? So I really do Cartesian product, or if you want tensor product. So given a set, I create a new, so given a ground set, I create a new ground set. The new ground set is would be n times n times n. So this is the points in this set are all vectors, right? There is an order matters, right? They're really vectors whose coordinates are the elements of my original concept. Right? So E1 of Gn means vector whose the first coordinate is E1, the second coordinate is E2, and I take the collection of all such guys such that every coordinate was an element of it. Right? So again, right? So I really like imagine, right? If your set was, right? Example. So if your f was 1, 2, then G of f will contain vectors 1, 1, 1, 2, 2, 1, and 2, 2. They're all the same. Right? It's just Cartesian product of the sets. Ready?
This condition S for all s less than or equal to m minus 1, it's clearly sufficient. Is it in some senses necessary?
I mentioned this before, right? So you remember even for when m equals 2, right? If you tell me that you don't cover your ground set, then of course I can take, let's say, triangles all sharing one vertex and then add one vertex to make my ground set even. Otherwise such things exist, right? M minus 1 is really necessary.
I see. So
For any
that
prime
was,
I can...
for every m you can do...
Right. So if, for example, if m equals 3, so maybe, like, let me have here an example, right? So if my m is 3, so here is a picture, right? So how many points we have? My m is 6, m is 3. So I have a family of sets, all have size 2 mod 6. The intersection, all intersection has 1 mod 6. Ground set is 0 mod 6, and such things exist, right? And why it exists? Actually knows that I cover completely ground set. Why it exists? Because I don't cover sets of size 2. And I can cook such figures. So it's really a minus 1 is necessary. You also see it in the proof, and it's also because it exists. So any questions?
Because here you miss many sets of size n minus 1. So,
Sorry?
but here you miss a lot of sets of size n minus 1.
I mean,
For example, to go back to Madhu's question, here you miss quite many sets of size n minus 1. Maybe if you just miss and you have
but I mean, in this inclusion-exclusion principle, you see that it's really important that I cover everything, right? Because there is an equality, right? Maybe if you tell me some parity what I miss, but it would be much more complicated. Then I really need to look on the system. And when I do inclusion-exclusion, I don't look on anything, right? I know ground set, I know all pairwise intersection. These guys are even, these guys are odd, right? It cannot be equal. So it's much.
But so just to belabor this point, in the simple odd even case, if I know that all intersections except for one are fine, does that mean immediately that you can actually have such systems?
Maybe I need to look, right? Okay. I need to look, right? It's somehow, we didn't elaborate too much on this problem because you'll see that first of all it's kind of very pretty and kind of very concise. It solves what we need, is quite natural. And also there is still, even here, things to do, right? Before you go to like a maybe more, but it's a natural thing. It just somehow didn't. So now let me kind of indicate how you can push it further, right?
So why didn't you take this to arbitrary composite numbers by taking it to the total number?
Sorry?
Other odd numbers.
So arbitrary, instead of m being a prime, I guess take an arbitrary number and just take everybody to the total.
It's all taken care of. So just bear with me another 10 minutes, right? You'll see what's the problem with the composite numbers. Okay, so maybe let me delete it. So we already know what is n minus 1 system. So let me now indicate how you can go further. So now you understand the approach, right? I take a set system, I massage it in some way by taking some kind of product to get a new set system or a new ground set, and I try to move all residues, which were very different, to somehow to the same residue, right? So now my n is a prime power, right? So now my n is okay, and somehow what can I do? So there is a different transformation in addition, right? So tensor product or Cartesian product give us powers. So it's another very natural transformation. Nothing of this we invented, right? It was using combinatorics for many years. There's another very natural transformation with the system you can do, which gives you binomial coefficients, right? So what I can do, for example, I can do this. Right. So my n would be n choose I, right? My original set choose I. And moreover, for every set f of size x, the g of f will have size x choose I. Again, what would be the transformation? So given f,
You take I equals P, or
sorry?
I will be P or something.
No, I'll just want so far tell you what I can do, right? And then we will play with it, right? I'm just trying to see what kind of transformation with a set system I can do, right? This is an interesting question. How I can move set system to get new system with a different kind of properties, modular residues. So now for every f, I take a new set, right? New set containing as elements all subsets of f of size. So again, you give me a ground set, I create a new ground set where it would be all I element subsets of n, and every set will become a new subset where I take all I element subsets of n. Now this is one thing I can do. I obviously can do another thing which you can do, so this is maybe one. I need one more thing. Again, you check, right? I will not go into this thing, but you check that it preserves intersections and things like that, right? So that image of intersection is intersection of images, and so on. Now another thing which I want to do is you can add transformations, right? That's the last thing which I will need, right? So if I have G1, which is 2 to the n from 2 to the n1, and I have a transformation G2, which is from 2 to the n to the 2 to the n2, right? And this guy, the size of the set x gives me G1 of the set, the size of the set x becomes G2 of the set x, right? So for example, you take, x squared and x choose 3. Then I can create a new family where the subsets of size x become of the size x squared plus x choose 3. And again, it's very easy to do this. You check that all things are preserved. You just take disjoint copies, right? Ground sets. So these guys, obviously, you can take them disjointly, and then G of f would be G1 of f union. And obviously, if you need to multiply by scalar, you again, it's like a sum, you take. Okay, so what basically we learn now? So we learn that starting from any family, you give me this function g, which I can combine from these things, and then I start with my ground set, and I create a new ground set, such that all sets would be transformed precisely in that way. And so what I want now, I want a polynomial, which I can build like that, which for m p to the k, which will do the following, and that's possible to do, and it was known that it's possible to do. For example, if you take a work, one place where you can see work of Baring on voting polynomials. So I think they, for example, had such transformation. But again, they maybe did it in a different way, but you kind of see this polynomial. So I want a polynomial, g of x, which I can write in this form, such that for every x which was 0 mod p to the k, the outcome would be 0 mod p. And for every number which was not 0 mod m, it will become, let's say, 1 mod p. Right? So note that from p to the k, I'm moving to mod p. Right? And there is a very, right, so there is a very easy and explicit polynomial. So here's the lemma. Right? So take a polynomial. You need elementary number theory to prove it. So take a polynomial g of x, which does the following. It's x choose I where I between 1 and n and I is odd, plus p minus 1, p would be the same p there, sum of x choose I, where again I between strictly less than m, so strictly less than m, strictly less than m, and I is p. And then the claim is g of 0 is 0 mod p, and g of x is 1 mod p if x was not 0. If x was not 0 mod p. And I claim that this does it for you, right? Because, so believe me that this lemma is true, it's not very difficult to prove. So first thing you're proving that this binomial coefficients mod p, so you can basically take x and first reduce it mod p to the k. So whatever multiple of p to the k you can remove. So you can assume that your x is less or equal than p to the k, less or equal than m, and then you just substitute it and you just see that it's like a expansion of binomial form. It's like 1 minus 1 to the power size of x. It's very easy to check. A little bit numbers.
There is
But
this formula. I forget.
There is a formula, but as I said, it's really, you even don't, right? It's originally what I taught to you. No, but then we saw that you don't even need a formula. It's really very elementary for this polynomial, right? So this is very elementary to check. And now what you'll do, so you give me this, right? So you give me this, so given m minus 1 system, so you do transformation G and you transform it into system such that, right? So the size of the image of the set would be precisely G of F. Right? So therefore the ground set would be 0 mod p. So the n, right? The n would be G of n would be 0 mod p. So these guys would have size 1 mod p. And moreover, because how we do the transformation, note that this transformation, even with a binomial coefficient, if I knew that there is a set which contains every subset of size I would cover the ground set, right? Because in particular, this element would be a point in G of F, right? So if you want, right, so you want to, the important thing was to cover the ground set there, right? So if you look on this transformation, and you're asking, am I covering all I element subsets of the ground or here, right? Am I covering all points here? It means you're asking, am I covering all I element subsets? If you, for every I element subset, you have a set which contains it, in its image of the set, you will cover this
It's
point.
important that the degree of the polynomial
Is at most m minus 1, right? So note that the degree of this polynomial is at most m minus 1, so therefore, because of the condition on n minus 1, we cover this. Okay. So and that completes the question.
So when k equals 1, is this doesn't or
Wait,
does
what
it
is
turn
k?
out to be so m is p to the k, right?
Oh.
So m is prime.
So when m is prime, does
Right.
does this turn out to be kind of equivalent to what was done before, or is it a different?
It's a bit a different polynomial, right?
Does it suggest that there's some additional freedom that's not being exploited because you also
Okay,
have?
so Kravitz question, right? So this is a Kravitz question, and we come to the question which was already asked several times: why we stop at p to the alpha, right? So it looks like there is a lot of freedom here, right? So you go to sleep, you dream about some magic polynomial which takes these numbers, does something to them, right? Let's say there's an open question, right? It's a question. This is really a good question, right? So 6, 5 systems are there, right? So m equals 6, right? So are there, right, can I prove that they do not exist like that? And the answer is no, right? Or at least looks like no. So let me tell you why the answer is no. So imagine you would knew how to cook this polynomial, and the polynomial is of low degree, of constant degree. So you would know how to cook the polynomial, which will take, right, so you will have a polynomial, so g of x, polynomial of constant degree, such that g of 0, g of x is 0 if x was 0, not something, not some p, right? We need to choose this prime. Probably it would be either 2 or 3, right? It would be one of the primes which divide m, where x is 0 mod 6. And maybe it's equals to, let's say, 1 mod p when x was not 0 mod 6. So imagine you would have it. So then you can take any set system and apply it. So now there is a very nice result of Golmus. So actually it was known that set system was restricted. So this is what I studied with, right? This Berlekamp result. It's an example that set system was restricted intersection modulo prime have polynomial size. Right? So if you tell me that you have sets whose size is 0 mod 5, but all pairwise intersections are not 0 mod 5, and you ask how many such sets are there, the most m to the 4. So they're polynomial. But there is a construction by Golmus of set system which has size bigger than polynomial. So there is a construction, right? So there is a set system. Let me finish with that. So there is. So this is a Golmus. So there exists f, right, such that f has 0 mod 6, and f intersection f prime are not 0 mod 6. Right? And the size of f is bigger than, let's say, n to the power log n, thing divided by log n. But much bigger than any polynomial. Now, if you would have given me such thing, what prevents me to take this transformation and apply it to the system? Right? Then what I will get? I will have a set whose size was 0 mod something. It will stay 0 mod prime. And then the intersection will become 1 mod prime. And then I would know that the system should be polynomial in the size of a new ground set. But the new ground set is polynomial in the size of the old ground set. So therefore, none of these things. So it looks like none of these things, unless you're doing something very different from what we're doing, would work. Okay?
The question is, okay, can you use Gormless construction to construct this system?
So I thought a little bit, right? It's kind of hard to, so that would be kind of a first thing maybe to say, okay, maybe 6-5 system exists, right? It would be very unfortunate for our algorithm, but I think it's a very cool question from the point of view of the problem itself, and I think problem is right. I'll try to play a little bit. I didn't see quite how to do this because it's hard to control all the intersections, right? So Golmus controls pairwise intersection, then you have triple intersection, quadruple intersection. It's a bit hard to see how you do it.
You can try. Did you check if for very small value of
For very small Martin, I really have not good with a computer, but Martin.
Okay. Another question. So somehow I think the polynomial I know is m minus 1 choose x minus 1. Could it be that this polynomial, x minus 1 choose m minus 1? Could it be that this polynomial is good for you just as well? Because this is, for example, what we use.
X minus 1.
So I think
M is bigger than all these x.
But then how you, so you have a set of size.
This is a polynomial that I think for every x that is 0 modulo.
Yeah, no, I understand, but I want to take my set f, right? How I'm transforming it into x minus 1. Then you need to expand it, and that maybe roughly would be.
It would be
it's very convenient not to change x inside, right? Because you know you do transformation on the set. It's not just a polynomial.
Yeah, I mean this is of course again a polynomial.
But you can expand it, and then it would be more similar to what.
Because this one is very easy.
Yeah, I know. But we wanted a polynomial where, right, the variable is real x itself. Then it's very easy to see how. Right? Again, right, none of this is a kind of surprising thing. Right? People use this type of thing. It just, I think, the connection is interesting. And the problem itself, right, 6-5. It would be very happy to know just what the answer is.
You know, if it's possible to do some modular optimization, let's say where you restrict yourself only to sets which are 0 modulo square root n, if square root n, if square root n, let's say, is a prime. It's not a constant, it's something. You just want to minimize overall sets of some. It's possible, it's polynomial.
I'm not specialist, you can imagine. Like whatever we needed for this problem was nicely supplied to me by the market.
You suspect that in general not, because you said that it's hard if you give a lower bound.
If you have a one lower bound constraint, it's already hard, right?
A lower bound of a cardinality.
Low bound of a constant or a super
No,
constant.
Of a big. And if you take modulo, which is big
then
enough,
it's okay.
then
Then,
it's
okay, I see
equivalent.
what- yeah.
But maybe some-
So for these m-1 systems, is there something like if they exist, they must exist in a universe of this size? Can you prove some finite?
So we have certain bounds which saying that many things which you would find natural would not work, right? Something like of this type, because of the transformations, right? But right, it's a universe, right? Because Gromul's result will tell you that the universe should be big, right? And things like that. But they still might, right? Just if I don't tell you what the universe, take the universe super huge, right? If it exists, it shows that the algorithm might not work, right? So it's really a bit different question to compare to what people look in extremal sets. Just really existential question. Is there such
Right, but you
system?
can't somehow say it's a huge universe, it must exist over a slightly smaller.
Right. The universe should be big, right? That you can get.
More questions?
And from the proof, maybe from the proof your universe is not so big. If the algorithm does not work, you get some specific universe.
We didn't see how. We didn't see how.
Because you said that from the proof you would get some, if it doesn't work, then you
Then
get
you
something
construct, but it's like you
but you have
construct
no
over
idea
ground set
how-
n, right? Big means more in a
only
function
in
of
a
m,
function
right?
of
Like
the
not-
set, right? Yeah.
Now, one thing which I want to say is that, which again, right from, if you remember the algorithm, from the point of view algorithm, the only relaxation you can make is that obviously the algorithm, the set system, the polynomials you're using not necessarily need to be of size m, right, of degree m, they can be much bigger than m, and I also can allow you to cover not every subset of size m-1, but every subset of size 100m, because I just do more searches, right? It's the same.
So you mean, for you it would be okay if the polynomial...
Right, so for
bigger.
me, if you show me that 200 system does not exist, it would be as good, right? So it means that all subsets of size 200 become good, but we didn't see how it would help us.
So you talked about m-1 systems. Are other parameters interesting? Like if you take m, like m plus 1, or
Yeah, as I said, that's what I just said. You take m, 100m, show me that it does not exist.
So what
Because
do we
that
know-
would give me the algorithm still, right? With the power 100m as exponent.
So what do we know about these other systems so far? It's unworking.
All right, so let's go. Any questions in the break?